Okay, so in chemical periodicity, we will be studying most of the time the trends in the periodic table. Okay, and apart from that, we will be studying the periodic table physical properties, chemical properties. Okay, then we have oxides, then we have chlorides, and many more things. So we'll be studying those basically in the periodicity. So periodicity is basically what? Periodicity, we can say, is the recurrence of similar chemical properties, okay, that occur when elements are arranged in increasing atomic number. By definition, periodicity is recurrence of similar properties. It could either be, physical or chemical at regular intervals when the elements are arranged in increasing atomic number. So what are we basically talking about here is the periodic table. So if we look into a periodic table, let me show you one periodic table. Okay, here it is. So this is one of the most basic periodic table. Okay, so you can see that the periodic table is divided into blocks. Okay, what are the blocks? Like the first group 1 and group 2 are known as S block elements. Okay, then the group from group 3 to group 7, these are known as P block elements, and group 8 or group 0 is known as noble gases. Okay, and this, okay, D block, these are what? Transition elements, transition metals. What do we call them? D block elements. And these are lanthanide and anthracite series that start from here. Okay, that are continued from here. Like nice series are from continued here. You can see that it is 57, then it is 58, 59. Okay, and then it is 89, so it starts from 90, 91, 92. So these are the continuation of these series, but they are in a separate uh, column, that is F block. Now why do we call them S block, P block elements? Because by the electronic configuration, if you have studied, okay, in the first chapter, if I look into the electronic configuration, so all the group 1 elements and their configuration on S1. Okay, then all the group 2 elements and their configuration on S2, no matter what is their shell number. Okay, but they end their configuration on S2. For example, if I take sodium is what? 11. So one S2, then you have 2s2, then you have 2p6. Okay, now this is how much? 4, 4 and 6 and 10. Okay, now 3s1. So I can see it ends at 3s1. 3 is what? 3 is the number of period number, you can say, a number of shells that it will be containing, that element. Clear? And for p block, so group 3 ends in p1, then this is at p2, p3, p4, p5, and group 8, that is group 0, ends at p6. That is why their electronic configuration is always completed. Okay, that is the reason. So from p1 to p5 is our p block element that contains group 3 and 3 till 7. Now for the d block, same concept. Okay, it is like d1, d2, d3, d4, d5, d6, d7, d8, d9 and d10. This is another D block. Okay, we're going not going to discuss F block because that is not included. Okay, so this you just need to know that Latinite and Actinide series are started from are included in the F block elements. So this is one of the basic distribution of our periodic table. Okay. Now we're going to study some of the variations. Okay, so for the variations, first will be the variation in atomic radii, that how the atomic radii is being changed, okay, across the I'll just place the heading of variations. And this in first our variation will be atomic radii. Okay, now what is atomic radii? Atomic radii is basically distance, okay, half the distance between the nucleus, okay, two like atoms. So we have many type of radius. Okay, radii is the plural. So you have many say type of radiuses. For example, you have covalent radius, you have metallic radius, okay, then you have van der Waal radius. These are many different type of radii, but what do them? We make a general name for them, okay, and keep them in a single definition, that is atomic radii. So I'll just write atomic radii is the distance from the center of nucleus to the outer boundary of its electron cloud. Okay, this is one of the definitions. There are multiple definitions of atomic radii. I'll just copy one image and I'll paste it. Okay, so you can see that this is an atomic radius. Okay, you have two nucleuses, and from one nucleus center to the boundary the electron cloud. Okay, that is outside. And what is the above? That is internuclear distance. That is distance between two nuclei. That is internuclear distance. Okay, clear? So what will be the trend? Okay, what will be the variation in the periodic table? So if we see across period, okay, and across our group, okay, we will be seeing that. So if we look into across period, okay, so across the period, let me show you one diagram. I'll just keep it here. Okay, we can put it here. Okay, you can see the diagram. This shows the atomic radii, which means the atomic size of the elements across the period and down the group. So down the group, I can see that the size is increasing. The okay, so the concept is basic, it's very easy. That each time, the number of shells are increasing as we go down the group. So that increases the size of the atom. However, across the group, okay, sorry, across the period, the number of shells remains same. So if it is 3, then all these elements will be having 3 number of shells in their element atomic structure. So as the number of protons are increasing, okay, because the atomic number is increasing, so number of protons are increasing within that same size. So what does that do? That increases the nuclear charge. Okay, because this is an atom and this is our nucleus. Now the nucleus charge is increasing, which means it will attract more strongly the outer electrons. Okay, and that results in what? A little bit smaller element atomic size each time the atomic number is increasing. Okay, I'll just write that concept here. The atomic size gradually decreases This is because the nuclear charge increases with increasing atomic number, and one thing more, the shielding effect remains same. Okay, what is the shielding effect? Shielding effect is, do you know about shielding effect? So shielding effect is like this. You have an outer shell and you have one of the inner shells. Okay, this is one of, it can have multiple inner shells, but we'll be talking about the outer shell and the one which is just right below it, inside it. So this is the nucleus. What is happening here is you have electrons here, two electrons here, two electrons here, okay, something like this. But you know, the outer shell can either be completed or not. It is not necessary that it will be fully complete, but we are guaranteed that inner shell is always completed with 8 electrons. So what does it do? That these, because now they both are negative negative, okay, so what it happens here is these inner electrons do a repulsion, okay, on the outer electrons. So they try to repel these electrons due to a method called concept, that is mechanism, that is spin pair repulsion. Okay, so these electrons, this is electron 1 and this is electron 2. So this electron will move like a spin, okay, like this electron will spin like this. They though both spin in the opposite direction, they create a repulsion, and that repulsion affect these outer electrons. So what happens that, you know, nucleus is attracting all the elements, okay, sorry, all the electrons, whether it is inner shell, outer shell, it is trying to attract all. So this, due to the shielding effect, okay, what do you call this shielding effect, this repulsion, the attraction to the outer electrons, what happens, it weakens due to the shielding effect, okay. But in our case that does not happen, because the shielding, because we know now shell number is same, okay, if it is 3, the nucleus is always you know, at a equal distance. So in this scenario, shielding effect is across the period, you always have to remember shielding effect remains constant, okay. Down the group you can see the shielding effect increases because the nucleus is getting more far away, further distance away from the outer electrons, okay. So it will be more difficult to attract it due to shielding effect. Clear? So we'll look into that more in detail in the atomic structure chapter, but now I'll just write the shielding effect remains constant, and finally are attracted more towards the nucleus, making the atoms smaller. Okay, that is a variation across the period in atomic size. Okay, I have written here atomic radii, and you can also write it here atomic size. Okay, you can consider that as well. Now, next variation that we will be studying is ionic radii. Okay, now for ionic radius, we will be studying okay, I'll show you one diagram. Okay, see this diagram. So in this diagram I can uh, clearly look. Okay, so in ionic, which means now we're talking about the ions. Okay, so we know now that every element, okay, except group 8, that is not included in the periodic table because it does not react, every other element will be forming an ion. Okay, so in this scenario we'll be discussing only group S block elements and P block elements, okay, not D block. So group 1 and group 2, they contain the, and group 3, they contain usually the metals. Okay, group 1 and group 2, we are confirmed that they contain only the metals. So metals always have the tendency to form cations. Okay, they will always do what? They will always lose electrons. Okay, they will never gain electrons. So they always have the tendency to form positive ions, that are the cations. On the other hand, group 6 and group 7, group 5, okay, group 5 should also be here, but okay, it's just explaining a trend. So these groups have the tendency to form negative ions, that are the anions. Okay, and we can see that they will always do what? Attract and gain electrons. Now now cations, if oxygen, you have Na. Okay, so Na have how many shells? One, then okay, then you have two, then you have three shells. This is Na, but because Na has 11 electrons, the outermost electron, the outermost shell has only one electron. Now if I want you to draw Na plus, okay, Na plus, that is 10. Now the outer shell will be not included, because if the outer electron has gone, what will the use of the outer shell? Okay, so that will be gone, and we will be having only two shells remaining. Okay, so what does that mean? That cation will always form a smaller ion compared to the normal atom. Okay, compared to the normal element, we can see that. So the cation will always be smaller compared to the original atom. Clear? And what about anion? And reason? Hmm. Okay, gain more electrons. What does that do then? So the protons become less. Okay, like if you had chlorine, or you can take sulfur for example. Sulfur, if its sulfur is 16, now sulfur 2 minus will be 18. Okay, in this you had proton 16, electron 16, but now you have proton 16, electrons 18. So now the nuclear charge will be weakened. So the electrons, now the concept of shielding effect will work here, if you remember. Okay, so the electrons will be moved further away from each other due to weak nuclear attraction. Clear? So now we got the concept that cations will be greater, larger in size. Sorry, cations will be smaller, anion will be larger in size to compared to their respective atoms. But if we study the trend, across down the group and across the period, down the group still we are seeing an increase, because shell number will be increasing, right? So down the group, the concept, the trend is same, that it will be increasing. So the ionic radius down the group will be increasing. Across the period, there is some variation. So, for example, if we see the period 3, so the cations, okay, we have cations from 1 to 3. These are decreasing in size. Okay, because we already knew that across period atomic radius was decreasing. So the cationic radius, okay, what do I call it? Cationic radius will be also decreasing. But as soon as we move to the anionic radius, to the anions, they will be slightly increasing. Okay, very slightly. This will be increased. Okay, now this will be increased, and again we can see the decreasing pattern. Okay, so from aluminium to sulfur we'll have a increase, then again we will follow our same trend. Okay, we will be following our same trend of decreasing. But just to show that, always show what, that cations are always smaller than anions, we have done this thing. Now let me show you another diagram. And these diagrams are usually important. The one I will be showing you for the MCQs, you will see quite a lot of them in the MCQs as well as P2. Okay, first look this, the axis. Okay, first study the axis. On the axis we have radius. Okay, so radius will be of the, we have both. Okay, the normal elements as well as our ions. Okay, cations and anions both. And on the lower level we have just the elements themselves. So for for the first basic Na, we can see the Na normal has a greater radius than the Na plus, because we have also already studied that cations are smaller than their respective atoms. Same concept for Mg. Okay, same concept for aluminium, same concept for silicon. Silicon is from group 4, so silicon is likely to form, okay, in our example, silicon will be likely to form a cation. Okay, clear? Now, as we move to the cations, now the cations are greater in size than their respective atoms. But again, we see what? A downward trend of decreasing. So this is a huge gap, okay, between the cations and anions. That is why this side graph shows a huge gap, huge size gap between these two. So the diagram has both variations, okay. You need to remember the variation, the trend, okay, basically of these, and then of these two as well. Okay, I'll just write some information here. We'll write one question, that why anions are bigger than cations. Okay, then we'll write the reason that cations are smaller because they loses a whole layer of electron. So the remaining electrons are attracted more strongly by the same nuclear charge. So the protons are same but the electrons have decreased. So the nuclear charge will be more strong now. For the that is why, okay, that is for the same both cations, why the cations are smaller than anions, and why cations are smaller than their respective atoms. This is for the same, okay, this could be the reason for both scenarios. For anions, they are bigger, okay, because they have more electrons and protons. Okay, and apart from that, we can write that the electrons are held less strongly by the nucleus. And one more reason will be the repulsion that is created when a new electron is introduced. This will be the reason why anions are bigger than cations. Okay, so now we have, and we also have to write the trend as well. Okay, now across the period, okay, we can see that always the radius is decreasing, no matter it is the normal elements or the ionics. So okay, the ions always they are decreasing. Why is that so? Because these are isoelectric. What does isoelectric means? That have same number of electrons. Okay, so the across a period all the elements are isoelectric, isoelectronic, we also say that isoelectronic. So ionic radius will be decreases, okay, gradually. This is because same electrons, okay, I said isoelectronic means same number of electrons. So electrons are same, okay, but the protons are increasing. Okay, protons will be increasing, that is results in greater nuclear charge. Okay, I don't think so, no need to write, but you just have to remember these, okay, trend. Clear? No, not exact values. Just study the trend, okay, that how the the radii are going downwards. Okay, yeah. Okay, then we have the variation. Our third variation is in melting and boiling points. So for the melting and boiling points, again we will be, okay, seeing one diagram. Let me just paste the diagram. Okay, again see the axis first. Y axis we have melting point, then we have proton number. This is group sorry, this is period 3. Okay, so because in this way, in this chapter, whole chapter, we will be seeing the trends across the period, not down the group. Okay, I am teaching you down the group as well, the concept, because that is also included in the atomic structure, but not in this chapter. Okay, we will study that more detail in the atomic structure chapter. Okay, so now look into this. Now we'll just explain it. Okay, so across the period, first see from sodium to aluminium. Okay, sodium to aluminium, I am seeing a general increase in melting point. Why is that so? Because sodium to aluminium, we have metals, right? So Mg, so the aluminium has a greater metallic bonding, stronger metallic bonding compared to Mg. Mg has more stronger metallic bonding compared to sodium, but less than aluminium. So what are we considering here? Metallic bonding. Okay, because these are just atoms, right? They will be metals. So metallic bonding is being considered here. The more the outer electrons, okay, we know na, in sodium has only one electron, so it will form a positive ion. Okay, like this will be a metallic bond. Have you studied this? We can make, like, circles around them, and there will be one outer electron, like this. But for the same, if we draw same structure for aluminium will have one aluminium cation will have three electrons outer. Okay, that will form the sea of electrons. So who will be having more metallic bonds stronger? Aluminium. That is why aluminium has a higher melting point, and we can see a increase, general increase. Clear? Then we have silicon. Silicon has a very direct peak, okay, and highest melting point. Why? Because it forms a silicon itself, okay, forms giant covalent structures. If you remember in chemical bonding chapter, you have, okay, SiO2. So that is the reason it has a high, very high melting point. So lot of energy is required to overcome the strong covalent bonds that it forms. Then you have again, okay, then we see a sharp decrease because now we have entered the non-metals section. Okay, so first we can see that all these are lower. Okay, even from the aluminium, these are lower. Why? Because they are simple, they form simple covalent structures. Okay, that is the first reason. So they all have lower. If we study within them, okay, this trend, we can see phosphorus has a lower one, but why the sulfur has a slightly increased. Okay, the reason is that because if you see, sulfur remains in the form of acid. Okay, so sulfur has the highest melting point. Then which is next? P4. Okay, phosphorus remains in the form of P4, not P. Chlorine remains in the diatomic Cl2, and then you have argon. Okay, so what force is considered here what force is influencing melting point, that is van der Waal. In the van der Waal, you must have studied that the more electrons there are in van der Waal, the stronger the van der Waal will be. Okay, so acid has more electrons than P4. P4 has more electrons than Cl2, and so on. So the more electrons we have, the more stronger will be the van der Waals in the non-metals. That will result in more energy required to break that covalent or non-metal structure, non-metal bond. Okay, so basically we will be breaking down the van der Waals in this intermolecular forces. Clear? I'll just write it. For this you have to remember, okay, try to remember each and every dot, how it is being made here. Increases from Na to aluminium because strength of metallic bond increases. Then we have silicon has highest melting point as it forms giant covalent structure, so require lot of energy to break the bonds. And then we have melting point of PSCl and argon are lower because they form simple covalent structure only weak van der Waal exist for them. And if we study between those, okay, so melting point of phosphorus is, oh sorry, sulfur, then you have phosphorus, that is greater than Cl2 and that is greater than argon, because number of electrons because as number of electrons increases from argon to sulfur, the van der Waals becomes much stronger. Okay, now we have variation in electrical conductivity. Okay, for electrical conductivity, again we will be seeing one trend diagram. Okay, so for the electrical conductivity, I know you have some idea that if we can see that from Na to Al, we can see an increase in electrical conductivity because same concept, these are matters, they will, the more electrons they have in their outer sea of electrons, the more higher will be the electrical conductivity, because who will conduct electricity? Electrons will conduct electricity, right? So they will have more outer electrons in the sea of electrons. So aluminum will have, like 3 per cation, 3 electrons per cation. Mg will have 2, Na will have 1. So highest electrical conductivity will be found in group 3. So then we see a decrease because now these are all non-metals, so they will not have any free electrons, okay, delocalized electrons. So they have very negligible electrical conductivity. And so far as silicon is considered, silicon is a semiconductor. Okay, so there is a some chance that it will do the electrical conductivity because it's semiconductor, not a full conductor. Okay, clear. Across the period, Na to aluminium, electrical conductivity increases. Reason will be number of electrons contributed, number of electrons contributed per atom to the sea of delocalized electrons increases from Na to aluminium. So more electrons to conduct electricity. And from silicon to chlorine, I'll write that silicon is a semi metal because it has some properties of metallic properties and some non-metallic. Semiconductor, and remaining elements do not conduct electricity. Because there are no I would say mobile electrons. Mobile means free electrons. Okay. Now our last variation, that is in the ionization energies. For the ionization energy, that will be studying in chapter 3 as well. Okay, so for the ionization energy, we will be studying this in more detail, but I will teach you, okay, in this chapter as well. So I'll just remind you when we come to the atomic structure chapter, then we will not be studying that again, okay? So that will save a lot of time. So we'll just so we'll just study it here. So you can see that first in the first it is period 3, but it is a bar chart, okay? So first, ionization energy. Do you know what is ionization energy? Energy, yeah, energy that is needed to remove one electron from each atom in 1 mole of atoms, okay, in gaseous state. So basically we want to remove electron, one electron, first electron from the, so we'll be studying just the first ionization. शोर नहीं करो यार, ये किसका है? आपके लिए करना है, देखते हैं। So in the first ionization we can see every time across the period the ionization is increasing. Why is that so? Because what could be the reason? That proton numbers are increasing. Okay, so if the proton number are increasing, which means nuclear charge is increasing. Nuclear charge increase, okay, and we know that atomic size decreases, okay, across the period the atomic size decreases. So atomic size is decreasing, nuclear charge is increasing, so it will be more difficult, okay, it would require a lot of energy, more energy to remove one electron from the outer shell. Okay, that is why shielding is same, so I'll just write that. Okay, so is it clear? That is why we can see the first ionization. Okay, if you now look into the second diagram, period wise the first ionization is also increasing.